In this presentation, we introduce a method for learning off-road terrain traversability that utilizes only self-supervision, enabling it to learn traversability in various unstructured outdoor environments easily. Estimating the traversability from visual images is essential for autonomous navigation systems operating in outdoor unstructured environments, as RGB images can provide semantically rich information about complex environments. Numerous approaches utilize large-scale human-annotated datasets, which can be unsustainable and erroneous. As these datasets only contain observation for a specific and limited context, traversability estimation in off-road environments with varying visual appearances frequently leads to unreliable results. To learn the terrain traversability, recent research has focused on self-supervised learning methods that leverage a vehicle's driving experience. While it is impractical to manually annotate images of every single environment, labels on traversable regions can be automatically generated by projecting the vehicle trajectories to the image plane in a self-supervised fashion. This self-supervised traversability label can be easily obtained for learning traversability in diverse off-road environments. In this work, we propose a self-supervised traversability estimation method that learns traversability only from self-supervisions without any explicit labels. On captured data, the wheel contact points are considered traversable, and the occluded trajectories are filtered to eliminate false positive labels. As noises at LiDAR points are regarded as obstacles, the unsupervised LiDAR denoising is performed to improve the efficacy of filtering in off-road conditions. Trajectories are then projected to image coordinates and labeled as traversable, and the remaining pixels are left unlabeled. Since no labels for non-traversable regions can be obtained, we aim to identify traversable regions accurately only using this label without any kind of manual annotation using the one-class classification algorithm. For the one-class classification algorithm, the image is augmented and forwarded to a feature encoder. As there exist various representations of traversable regions in off-road environments, the representations of positive pixels have high intra-class variation. Therefore, the 2D normalizing flow, fast flow, is used to project complex distributions of features to a simpler distribution while avoiding a trivial solution. Then, the feature embedding space is learned to maximize the cosine similarity between the features of traversal pixels and a positive center. In addition to using positive data, we also utilize unlabeled points to obtain more discriminative features and also prevent hypersphere collapse. The flow features of unlabeled pixels are jointly self-labeled and clustered with a set of learnable prototypes motivated by self-supervised clustering method for learning visual representations. The feature space is learned by fully utilizing both positive and unlabeled pixels, enhancing the discriminative power of features for the one-class classification. However, the learned representations are still insufficient as the self-supervised label has limited supervision. To supplement the representation power of features, the encoder is simultaneously learned with the contrastive pretext task of self-supervised visual representation learning. Using the features of augmented images, the contrastive loss pulls features of positive pairs while pushing away the features of negative pairs, resulting in more semantically meaningful and discriminative representations for traversability estimation. After training the network with self-supervisions only, the network can accurately estimate the traversability of image pixels in real time for inference. After forwarding the image to the encoder and the flow model, each pixel's traversability is determined by measuring similarity with the positive center. We conduct experiments using our own dataset and Rally 3D dataset. Here is the results of experiments using the publicly available off-road dataset Rally 3D. Instead of merely assessing terrain type based on texture, our method can identify traversable regions more clearly and accurately, which are also contextually more significant compared to the results of other methods. We also use our own dataset gathered under a wide range of conditions, including varying places, seasons, weather, lighting, terrain types, obstacles, and lens conditions. Our method outperforms models trained with manual labels in a supervised way using public dataset. Due to the fact that our method exploits self-supervised label acquired directly on the target distribution, the model can estimate traversability much more reliably in the presence of distributional shift. Our method can effectively learn traversability in a wide range of unstructured and unknown environments. Using the flow model, our method can accurately identify traversable regions, that is, multimodal distribution, under the complex off-road environments. Please note that the method based on autoencoders produced a large number of false positives, implying that the simple reconstruction-based anomaly detection methods fail to accurately distinguish non-traversable regions. Our method produces fewer false negative occurrences than others, indicating that it obtains discriminative features for identifying traversable regions in complex off-road environments. We also conducted a quantitative evaluation. Our method shows a significant margin compared to other self-supervised traversability estimation method based on the one-class classification. We have also conducted ablation studies. The labels generated without occlusion filtering result in a high FPR, and the labels created without LiDAR denoising or shorter trajectories lead to a higher FNR. Also, the model learned without a 2D flow model or without clustering loss using unlabeled pixels lead to a trivial solution. Our method can be deployed in real time for high-speed off-road navigation. The estimation results are reprojected onto the bird's eye view coordinate using LiDAR point clouds to generate a traversability cost map. The traversability cost map generated from our method can accurately identify traversable regions that are safe to traverse.